Section 7.5, Strategy for Integration. For this section, you can do any 6 problems from problems number 1 through 82. You know what you want to practice, what you need to practice, and I'm giving you that liberty. As we have seen, integration is more challenging than differentiation. In finding the derivative, of a function is obvious which differentiation formula we should apply, but it may not be so obvious which technique we use for integration. So this is a quick highlight of all the different integration problems that are probably the most common. Obviously, this is not all of them, but check out the back of your book. There you will have all of them for sure. A quick note, when I took this course, my professor let us have a sheet with integrals to use during our quizzes and exams. I suggest you do the same. Build a sheet with integrals to always have handy as you work on all of your homework, quizzes, and exams. And also adding your own little notes to it as well. So here are some helpful techniques to working with integrals. First, you want to simplify the integrand if possible. Maybe you might have to distribute, as we see here on our first one. Maybe it's worth our efforts to work with our trigonometry to fit some of our trig substitution methods. Or maybe we have to change our exponents and use some trig rules. Second, look for an obvious substitution. Try to find a function where you can use maybe like a u sub to work with. Or if maybe we have to use partial fractions. Third, classify the integrand according to its form. So there's different forms we learned in the beginning of chapter 7. First of them is trig functions, how we can kind of manipulate our trigonometry, knowing that if we're taking the integral, we also need the partial derivative. So you need a pairing, right? Pairings such as sine and cosine, tangent and secant, cotangent and cosecant. Perhaps it might be worth our effort to use partial fractions. That's when we have lots of arguments of x, both in the denominator and the numerator. Maybe it's worth our effort to start by dividing and then continue with partial fractions. Integration by parts, then we have 2 arguments of x. If we have a radical, try trig substitution. Remember, we work when we have something squared and plus a number within a radical. And also, try again. Don't feel discouraged if you can't integrate at your first attempt. It takes effort, it takes time. Also, you're learning this at such a quick pace. So give yourself a chance to think, sit through a problem, digest what's going on, look through your notes, be very kind to yourself. It doesn't help if you're just so critical of the pressure of doing it quick. There's no rush. So let's talk about some methods of integration. For the first one, we see that we have tangent cubed over cosine cubed dx. Well, it might be worth our efforts to remember that the reciprocal functions. So if we have cosine cubed, we can write it as secant cubed. So that we make that change and we have that wasn't too helpful, right? Tangent and secant is an ideal pairing. Well, let's go ahead and write everything in terms of sine and cosine. Maybe that will give us a better effect. So tangent is sine over cosine, so we have sine cubed over cosine cubed. Secant is 1 over cosine. Okay, we see something going on here. So in the denominator, we can have cosine to the 6th power. All right. So then we know that we can continue because we have that pairing of sine and cosine. Now, if we're using sine and cosine, we need to keep, depending where you're making your u sub will be ideal. We need to keep one of them, the derivative of it, as an extra pairing. So let's go ahead and use a sine as an extra so that we have our integral of sine squared x, and let's have a sine left over, cosine to the 6th power x dx. Now we can let our u be cosine. Our derivative is now negative sine. We can write sine as 1 minus cosine squared. And now we can use our u substitution. So we have 1 minus u squared over u to the 6th power du. And now we can go ahead and write it as two separate terms. So that we have the integral of 1 over u to the 6th minus u squared divided by u to the 6th power. That's the same as u to the negative 4th, or 1 over u to the 4th. You continue from there. Our next example, we see that we have a function within a function. So here it might be ideal to use integration by parts. For this one, you might want to use the tabular method, or you can use a definition as well, whichever you prefer. All right, so here we can let our u be the square root of x, and the part that we're gonna integrate are db be the e to the, let's make it a u. Let's rewrite for a minute. Let's start by using a u substitution. So that we have our integral from e to the u. If we're letting u be the square root of x, then du is 1/2 square root of x dx. So if we're integrating with that, then we're going to need a 2 u du. And why do we have that u du? That's to make up this square root of x and the square root of x, since they will cancel. All right, let's work with this. So we have 2 integral of e to the u du. Now we have to integrate by parts. And by doing so, we're left with u, our derivative, our u prime, is 1. And therefore, our gb will be e to the u, so that b is e to the u. So we're using integration by parts. We're left with u, e to the u, minus e raised to the u power. Let's not forget that 2 in the beginning. So we have 2, our u was square root of x, e square root of x minus e square root of x. You can factor the e raised to the square root of x. So we have 2 times e square root of x times square root of x minus 1. This one was tricky because you had to do 2 different methods. You had to begin by use substitution and then continue using integration by parts. For the last problem, we see that partial fractions would be the ideal method. We see we have a fraction, and use substitution is not ideal because if, for example, if we let u be x to the 5th power plus 1, our derivative would be 5x to the 4th power, and we don't have an x to the 4th power anywhere in our argument, in our integrand. So partial fractions would be ideal so that we can write everything under a different terms, or it'd be an easier form of this problem. For the next one, we see that we have a radical and we have 1 minus x divided by 1 plus x. A helpful way to begin that I don't feel like we was practice enough is to rationalize the denominator. The numerator. If we do that, we have the square root of 1 minus x divided by the square root of 1 plus x, and we're going to multiply by the conjugate of the numerator, or by the numerator itself. So we have the square root of 1 minus x, the square root of 1 minus x, so that we have 1 minus x times the square root of 1 plus x, 1 minus x. Notice the difference of squares. And so we're left with 1 minus x divided by the square root of 1 minus x squared. And from there, we can go ahead and split our integral. Remember, it's divided by those 2 numerators. So we have 1 minus the square root of 1 minus x squared minus x over the square root of 1 minus x squared. And each one of these integrals will have to use a different method. So for this one, we can go ahead and use an identity using trig substitution. And for this one, because we have an x squared, we can just use u substitution. So that's the difference between those two. Now, of course, can we integrate all continuous functions? The answer is no, but we'll learn in the future how to deal with such type of problems. I think we'll see that in chapters 10 and 11. All right, that's it for 7.5. My biggest advice is just have all your integration techniques that we learned handy. Again, somewhere towards the end, middle part of your text, you have all of your integration formulas listed. Have that handy. That's it for this section. Your homework is 6 problems, any 6 that you choose, from numbers 1 through 82. Thanks.